Okay, so we started chapter 2 last time, and it was this was the first lecture. There are some slides that I didn't finish. I'm going to call it lecture 2 as well, 1 and 2 here, and if there is time, I will add more slides. Okay, so this chapter is about free vibration, and then we will be finding the natural frequency of in this free vibration, as well as the amplitude of vibration. So we started with the undamped system. Okay, and then we derived the equation of motion. Okay, which is obtained using Newton's second law, and make sure that the free body diagram, just one more thing. Okay, the free body diagram will be usually it contains kx and w, kx only because w and k delta will be they will cancel each other. So one of the common mistakes that usually is done by students is that the free body diagram, they put the weight without putting k delta, and then becomes one term extra. Okay, so this k delta, if you put the weight, it means you have to put k delta as well. Okay, so the free body diagram for vibration in for system arranged vertically, it will be only kx. Okay, so there is, if you put the weight, then you have to put k delta as well. So that's the free diagram in vibration. And then sum of forces will be equal to mx double dot, and this will be minus kx equal to mx double dot, which is this equation, same as this one. This equation is similar to what we did in chapter 1 about harmonic motion, and we call this equation as harmonic condition. Harmonic motion condition, which means that the second derivative is directly proportional with the negative of the original function. So x double dot is equal to minus k over mx. K over m is omega squared, but here we call it omega n because this is the equation of motion of free vibration, and the frequency in this case is called natural frequency. So n is subscript, which means omega n is is the name, that is the name of the frequency. And by checking the units, omega n square is 1/second square, or radian per second, radian square per second square. So it has the unit of frequency. And rearranging the equation this way, x double dot plus omega n square x equal to 0. This equation is second order ordinary differential equation with constant coefficient and is homogeneous. Then the solution is x equal to a sine omega nt plus b cosine omega nt. Regarding the frequency, the natural frequency is obtained by observing after you, this is say the final form of the differential equation. If you put it in this final form, then the coefficient of x is omega n square. So that's one thing we set as a as objective, is to find the frequency. So the frequency is obtained from this final equation without solving. So when you want to solve the differential equation, it means you want to find x for all time, okay, which is given in general as x equal to a sine omega nt plus b cosine omega nt. A and b are constants to be found from initial conditions, which are x at 0 and x dot at 0, which is initial displacement and initial velocity. So both of them might be not 0, or one of them might be not 0, is enough to start the motion from equilibrium. Okay, so in case both of them are not 0, then we have the final solution is x equal to x dot at 0 divided by omega n sine omega nt plus x0 cosine omega nt. Now the amplitude, if we just rewrite the solution here, x dot at 0 divided by omega n sine omega nt plus x at 0 cosine omega nt. Now if x at 0 is 0 and x dot at 0 is not 0, then amplitude will be, so x becomes x dot at 0 divided by omega n sine omega nt. Then what is the amplitude here? Amplitude is the coefficient of sine. Okay, and if x dot at 0 equal to 0, however x at 0 is not 0, then the amplitude, or x becomes x at 0 cosine omega nt. Therefore, the amplitude is equal to x at 0. But if both of them are not 0, then we have to write in different way. So if x at 0 is not 0, and x dot at 0 is also not 0, then we write x equal to, we use the trigonometric identities to write the solution. This is like expanded. So you can write it as a0 sine omega nt plus phi 0. Okay, where, by expanding, this, it means that a0 sine omega nt, okay, I'm going to write it, sine cosine phi 0 sine omega nt plus a0 sine phi 0 cosine omega nt. So you can see that a0 equal to, if you look at the solution, is equal to x dot 0 over omega n, and that a0 sine phi 0 is equal to x0, right? Because a0 cosine phi 0 multiplied by sine omega nt, which is the one that is multiplied by sine omega nt, is x dot at 0 divided by omega. And you can find you can write this a0 cosine phi 0 equal to x dot at 0 divided by omega n, and a0 sine phi 0 equal to x0. What is a0 and phi 0? You can square both equations. You get, and then add. So this is number 1. squared plus number 2 squared, and then adding. Okay, squaring both equations and then adding, we get a0 squared equal to x dot at 0 over omega n squared plus x at 0 squared. So a0 is equal to square root of x dot at 0 divided by omega n squared plus x at 0 squared. And that is the amplitude. And also we can get phi by dividing equation 2 by 1. We get tan phi 0 equal to x at 0 divided by x dot at 0 divided by omega n, which means we can put omega n at the top. Okay, so this is and then you can get phi 0, which is equal to tan inverse of x at 0 omega n divided by x dot at 0. It's called phase. Okay, it's phase. So this way you can get the amplitude directly from here. So this is the final equation that you need to get the amplitude and to get the phase. Okay, we can do this because we have sine omega nt here and cosine omega nt, which is the same argument. Okay, so anyhow, there are look, this is the way to get the amplitude. So in general, you can use this is the amplitude equation, right? And if one of them is 0, it will reduce to what we said in the beginning. So if x at 0 is 0, then a0 will be x dot 0 over omega n. And if x dot at 0 is 0, then a0 will reduce to x equal to 0, x at 0. So you can use this for all cases. Okay, so since the motion of the spring mass system is harmonic, then those equations are also valid. The natural period of oscillation is established from omega n tau equal to 2 pi. What is tau? Tau is the period of oscillation, which is the time required to complete one cycle. So this is a spring mass system. The spring will, if you can just relate this to what we did in chapter 1 about the Ch2 mechanism. And in the Ch2 mechanism, there was a spring mass system added on the top of the rod, which means that it will oscillate. Okay, so the spring mass system, this was in chapter 1. Okay, the spring mass system will oscillate with a frequency or period of oscillation. And that period of oscillation is the time to complete one cycle. So we talked about this before, and it is applicable here for the spring mass system. So it will be, as you can see, it is a sine wave. You can put it as a sine wave, which is a0 sine omega nt plus phi 0. So it is going to oscillate as a sine wave with amplitude equal to a0, and there is phase. The phase, it means if this is phase is 0, this is a sine wave, and we start with this is phi equal to 0. And if it is not 0, positive, it will start, as you can see here, this phi 0 is positive greater than 0. Okay, it's not starting from 0. So that is the phase. It is a sine wave. As you can see, this will continue as a sine wave with one period. This is tau here, and this is tau here. Okay, so the tau is the period of oscillation, which means the time to complete one cycle. So you put omega n t equal to 2 pi, we call t equal to tau. So when omega n t equal to 2 pi, we will give a name for that time. That is tau. So it is one period. It means that we have omega n t equal to 2 pi, and that t equal to tau. And you can write from this equation omega n tau equal to 2 pi. You can write tau equal to 2 pi over omega n. Okay, in chapter 1, this was the final equation, because omega was given as a number. Here, omega n is given as an expression, function of the system parameters, which are k and m. So you can substitute for omega n, then you get tau equal to 2 pi square root of m over k. And the frequency, omega n is also called a frequency, but it is called specifically circular frequency. And f is the frequency, natural frequency. So here also called natural frequency. Omega n, we called it circular natural frequency. Okay, so yeah, circular, natural, you can add natural frequency. Okay, so if n is 1 over tau, by definition, the frequency is the reciprocal of the period of oscillation. So it is 1 over tau equal to 1 over 2 pi after we substitute for tau, equal to 1 over 2 pi square root of k over m. And of course, you can also write that if n, omega n equal to 2 pi if n, this is also true, and if n equal to omega n over 2 pi, or equal to, when you substitute for omega n, it is equal to k over m. So if n is 1 over 2 pi square root of k over m. And from the static equilibrium equation, k delta equal to mg, or you can put k equal to mg over delta, and then substitute in Fn, you get that Fn equal to 1 over 2 pi square root of g over delta. Okay, delta is the statical deflection. Delta is statical deflection. And as you can see from this equation, that if you can only measure the statical deflection, you can find the natural frequency. So when you have a spring mass system, if we go back to the model, okay, from here, okay, the spring was with L0 before adding the mass. So when you add the mass, it will slowly, it will go to equilibrium position. And if you measure delta, then you can use delta in the equation of Fn to find the natural frequency. So without knowing how much is the mass, without knowing how much is the stiffness. Okay. Okay. Similarly, omega n equal to square root of k over delta, k over m also becomes g over delta. Okay. Example 1, a 1 over 4 kilogram mass is suspended by a spring having a stiffness of 0.1533 Newton per millimeter. Determine its natural frequency in cycles per second. So it is asking specifically to find Fn, cycles per second. Determine its statical deflection. Also, delta is required. So here is Fn is required and delta is required. Solution. The first thing you have to do is make consistent units to get the unit of the frequency. The unit of the frequency is hertz or cycles per second, and that can be obtained if you use the base units. So if n equal to 1 over 2 pi square root of k over m. Now we spent maybe almost 2 lectures about deriving Fn or omega n. So whenever we have a spring mass system, you just need to take the final equation for the frequency and as well as the amplitude if required. So you don't have to do the whole procedure. So as mentioned in the question, a 1 over 4 kilogram mass is suspended by a spring. So this is a spring mass system with mass equal to 1 over 4 kilogram and k equal to 0.1533 Newton per millimeter. So that is the question. And or this is the system. And the question is to find Fn and delta. So directly I will use the equation of Fn that we derived in the previous lecture. So Fn is 1 over 2 pi square root of k over m, 1 over 2 pi. K has to be converted to Newton per meter. Okay, so it is k equal to 0.1533 Newton per millimeter. You multiply by 1000 millimeter, divide by 1 meter. Okay, and it means that millimeter and millimeter cancel out and you get 153.3. Divided by 0.25, which is 1 over 4, we get Fn equal to 3.941 Hertz. The statical deflection can be obtained from the equilibrium equation, mg equal to k delta. Put delta on one side, which going to be mg over k. Okay, mg is 0.25 times 9.81 divided by 0.15. This is in Newton, right? Because it is the weight. And 0.1533 is a Newton per millimeter. Then you get the answer in millimeter, 16 millimeter. Okay, you can substitute for 153.3, then delta becomes in meter, and then you can do the conversion to find it in millimeter. Okay, so this is 16 millimeter. The question did not ask about the unit for delta, so you can find it in meter as well. There is no problem. You can find it in meter or in millimeter. Okay, so 16 millimeter, which is 1.5 centimeter. The spring, once the mass is added, it will go down. This is L0, and when the mass is added, it will go down 16 millimeter down. Okay, and And the vibration, of course, is going to be about this line. Now, this is the only two things required. There is no question about the amplitude here. That the amplitude is can be found if there is initial conditions. Okay, so there is no question about finding the amplitude, and there are no initial conditions given. So this is just asking for the nature frequency and delta. Remember in chapter 1, we talked about stiffness table. There was a stiffness table. Okay, and cantilever beam was one of them. So we get for members, and we can, and this is an actual system. So what you can do is model the structure as a helical spring. So you get K equal to 3EI over LQ for cantilever beam. Okay, determine, this is example 2, determine the natural frequency of the mass M on the end of a cantilever beam of negligible mass, shown below. So the beam is elastic, so it has modulus of elasticity. It has dimensions, cross-sectional area, and it has stiffness, and provided by, or can be measured by I, which is the moment of inertia. Now I, we don't have information about the cross-section of the beam, but it is just the only thing we know, it is its length is L given, just a parameter L, and negligible mass. Now the mass is negligible for the beam as compared with M, but this is not usually embedded, it's not mentioned. That the mass at the end here is very much higher than the mass of the beam, then you can neglect the mass of the beam. There is no zero mass, right? But as compared with the mass at the free end, you can neglect the mass of the beam. Okay, and this can be modeled. This is the actual system. This can be modeled as a spring with supported. This is the fixed, so it is fixed here. And this point is moving with X, so it is moving with X. Okay, K, we should get K equivalent. For the cantilever beam is 3EI over LQ. And the spring is massless. The natural frequency, it is required, determine the natural frequency. Okay, so you can find Fn or omega n. The natural frequency for this model is Fn equal to square root 1 over 2 pi square root of K over M. That's it. Okay, so this is just giving us the stiffness for cantilever beam is X equal to, this is the deflection under concentrated load, X equal to PL cube over 3EI. Now, if you search or you go back to mechanics of material, you will find that the deflection, if you just change everything, because this is X usually, is for dimensions along the length of the beam. So if you have a concentrated force here, P, applied at the free end, which is L, X equal to L. If you take, let's go back to mechanics of material. Okay, so there will be usually when in mechanics of material you will introduce X measured from the fixed position, and then this will deflect. The beam will deflect, and then you have Y, okay, to be function of X. So Y is function of X. And then there is equation. Now I don't recall the equation, but it is function of X. But at X equal to L, that Y equal to as given here, P L cube over 3I. So you arrange this equation in as Hooke's law, you put P on one side. This would be 3EI over L cube times Y. So this is the stiffness. This is K. Okay, now in vibration, usually we use X rather than Y. And X here is the deflection of the beam at the free end. Okay, it is the deflection. So the K is equal to 3EI over L cube, and then we just need to substitute in the equation of Fn. Fn equal to square root of 1 over 2 pi square root of K over M. K is a 3EI over L cube divided by M, and that will be the natural frequency, which has that K is given as an expression, which is function of the beam elasticity and geometry as well, which is I, neglecting the mass of the beam. Okay, so what we have here is actual system and modeled as spring band system. Okay, the main assumption then here is that the beam is massless. Okay, and K is assuming this is uniform, not mentioned, but should be uniform cantilever beam. Uniform maybe not as the equation given is for uniform. But if you have a non-uniform, what you need is K at the free end. That's what you need. The spring equivalent at the location of the mass. Okay, we can proceed. Example 3. Any questions? The column of water tank shown below is 300 feet high and is made of reinforced concrete with a tubular cross-section of inner diameter 8 feet and outer diameter 10 feet. The tank weighs 6 times 10 to the power 5 pounds with water. By neglecting the mass of the column and assuming the Young's modulus of reinforced concrete as 4 times 10 to the power 6 psi, determine the following: the natural frequency and natural time period of a transverse vibration of the water tank, the vibration response of the water tank due to an initial transverse displacement of 10 inch. C, the maximum values of the velocity and acceleration experienced by the water tank. So what you have here is a water tank and there is an assumption that the mass of the column is neglected. This is actual system modeled as cantilever beam with mass. Cantilever beam carries a mass at the free end. Okay, the beam is assumed to be uniform, so we can apply the equation 3EI over L cube. And the mass at the top is the mass of the tank with water. It's given equal to 6 times 10 to the power 5 pound, which is the weight given. And there are assumptions made here that from the actual system, we can see that the column is tapered, which means the diameter is bigger at near the ground. Okay, and also at the top. But most of it is uniform. So it is assumed to be uniform all over from beginning to the from ground to the tank. With a cross section, okay, it's tubular, which means it is hollow with inner and outer diameter. Okay, the inner diameter is 8 feet, the diameter. So DI is equal to 8 feet, and the outer diameter is 10 feet. And it is assumed to be uniform from ground to tank. So that is a cantilever beam assumed to be a cantilever beam with uniform cross section fixed at the bottom, and then it is carrying a mass at the top. That is the model, first model. Okay, the second model is that this will be a spring and mass. Now, the difference between this system and what we did last time, it was the spring was vertical and the mass is hanging. Okay, here it is horizontal. And this is, as far as the vibration is about equilibrium, it doesn't matter if you arrange the system as horizontal or vertical. Okay, so you can just add here rollers, and then this will be X. The initial frequency for this system is no different than a vertically arranged system. If n or omega n is square root of k over m, or if n equal to 1 over 2 pi square root of k over m. Okay, so we are modeling a spring mass system. And once you reach to spring mass system, there is no need to make derivation for omega n or fn. You can use what we did, it is already derived. But here, cantilever beam, K is equal to 3EI over L cube. So you will find you use K equal to 3EI over L cube. Okay, so we will work, there are some numbers given, so we need to work on calculating those parameters and then substituting in this equation to find the nature frequency. Okay, so this is the second model. And this is the final one. Okay, so the solution for part A. Okay, let me read this. Maybe there is something I missed. Assuming that the water tank is point mass. Okay, that is one more thing that this is one of the approximation. Otherwise, rotation is considered. If you consider that the mass, that the tank dimensions, it means that it is also in rotation, translation and rotation. But when you consider it as a point mass, you neglect the rotation. Okay, so this is one more assumption. The column has a uniform cross-section. This is the second. And the mass of the column is neglected, that is, or negligible. This is the third. The system can be modeled as a cantilever beam with concentrated mass at the free end. And we know that a cantilever beam, massless cantilever beam with the mass at the free end is a spring mass system. Okay, so to find K is already, we know, for a cantilever beam is equal to 3EI over L cube. And I is for a cantilever beam, if we go back to example 2, okay, I is, I didn't talk about I here because there are no numbers given. Okay, this I is just so I will put one comment that I is the moment of inertia in bending. Okay, you know that the I can be either about an axis or about we have either polar or about an axis. Okay, even polar is about a point if this is an area. So this is about bending, which means about an axis that is might be from the top view. You have to look about the cross section. So in general, if this is the cross-sectional area, okay, it will be about the centroidal, either this line or this line. Okay, so it is about bending. So if bending in this direction, okay, then it will be about this line, let's say Y. If bending is about this direction, then it will be about X. Okay, but I don't want to confuse you with the coordinates because already we are using X for motion, or just let me just make it capital Y and capital X. Okay, so the cross section area and the moment required is the moment of rotation. So there is Ix and there is or Iy. Okay, note this is point O, not Io. Io is polar, and that will be in torsion. In case we have torsion, that will be also part of this chapter. We will talk about torsional vibration. So we will need IO, which is the moment of inertia in bending. Okay, so those are in bending. IX or IO are in bending. And this is torsion. So for the beam, it is the vibration. It means you are putting load on the beam as bending. Okay, you're trying to bend the beam. So the moment of inertia is the one that is for bending. The same thing here. The moment of inertia will be in bending. Okay. So for circular cross section, I is pi d to power 4 over 64. But this is tubular, which is hollow. It means you have to take the moment of inertia of the outer minus the moment of inertia of the inner. Okay, so for solid shaft, solid area, I equal to pi d to power 4 over 64, which is the moment of inertia in bending. But for hollow, it means that I equal to I outer minus I inner. Okay, which means pi d outer to power 4 over 64 minus pi d inner to power 4 over 64. And then you can see that pi over 64 is common. And you get that I equal to pi over 64, which is common factor, d outer to power 4 minus d inner to power 4. Okay, do not do moment of inertia is d outer minus d inner all to power 4. No, it is moment of inertia minus moment of inertia. So it is pi over 64, d outer to power 4 minus d inner to power 4. The units we will use is, PSI, E equal to 4 times 10 to power 6 PSI, which means pound per square inch. The dimensions given are in feet. This d outer is 8 feet, and d inner is 8 feet, and d outer is 10 feet. So you need to convert the dimensions to inches so that you have consistent units. In K is you need to substitute in the expression for K3EI over L cube. Okay, so 3 E is pound per square inch, so it means that you need to write I in inch to power 4 and also L in inches. Okay, so 120, it means 10 times 12. So d outer is 10 multiplied by 12 is 120, and d inner is 8 by 12 is 96 inches. This is 120 inch, and that is 96. Okay, so I is 600.9 times 10 to power 4 inch to power 4. K equal to 3 times E, which is 3 times 4 times 10 to power 6 times I, which is 600.9554 times 10 to power 4 divided by L. L was 300 feet multiplied by 12, which is 3,600 inch. So dividing by 3,600 to power 3, we get K equal to 1,545.16 in pound per inch. And then you can okay, we need the rest. Okay, we will continue this example next time. I think we reached the end of the lecture. Okay, next thing is just to substitute in the equation for omega n or Fn. Okay, so we will do this next time, inshallah. Any question?
دكتور عندي سؤال بسيط.
تفضل.
نقدر نعتبر الناتشرال فريكونسي، يعني مثلا نقول ان الناتشرال فريكونسي equals to pi over jother ال deflection of static deflection.
pi over delta.
ايه.
ان هذه اف. لا.
يس.
لا. من وين يعني؟ لا، من وين دي المعادلة؟
والله يعني سويت يعني مثلا بعد هاي يعني حاولت ان افكك طلع لي كذي، وحليت الاكزامبل 1 طلع نفس الناتج دكتور.
example 1.
ايه دكتور.
اوكي example 1. انت الحين طلعت الدلتا، انزين، وقلت ان الاف ان يساوي اللي هي الباي اوفر جذر سكوير روت اوف دلتا.
يس.
ويطلع لك نفس الجواب بالضبط، يعني
نفس الجواب
3.941.
يس.
أنا ما أدري شلون دي صارت، يعني ما أعتقد إن إليها justification. بس من وين جبتها يعني؟ شلون بس فكرت فيها كذي؟
حتى طالعت من اليوتيوب بعد قال لي
إيه.
كذي.
أوكي. احنا عندنا إن هاي يساوي 1 over 2 باي square root of g over delta. أوكي، هلا نعرفه. بالنسبة إلى الجي over 2 باي، يمكن يعني فكروا في ذا الشيء، إن سكوير روت جي أوفر 2 باي، شوف كم يطلع لك بس. أوكي، يعني هذا الشيء بالتجربة يعني ممكن تسويه. يعني 9.81 تحت الجذر، أوكي، على 2 على الباي، يطلع 0.5 بعد، ما يطلع باي يعني. فما أدري شلون يصير. أوكي، يعني مو صح.
ما ادري مشكور.
أوكي، ما علم نشوف إن شاء الله خير.
ما
يلا،
تقصر.
حياك.